Hello students, today's class we are going to study multi-stage amplifiers, the definition of gain of multi-stage amplifier, bandwidth and frequency response of multi-stage amplifier. So by the completion of this class you will be able to know the definitions of gain of a multi-stage amplifier, bandwidth of multi-stage amplifier and frequency response, and also we are going to solve few problems related to gain of multi-stage amplifier, bandwidth and also the frequency response. In the previous class we have studied the classification of amplifiers and also the need of a multi-stage amplifier. So the need, when coming to the need of multi-stage amplifier, the gain provided by a single stage amplifier is not suitable to drive the loads. So no single transistor amplifier configuration satisfies the conditions required for practical applications. So for practical applications, the specifications are required for a general purpose amplifier should have high input resistance of the order of 1 mega ohm, high input resistance of the order of 1 mega ohm, and output resistance should be very low, and it is of the order of only few ohms, that is 100 ohms around, and voltage gain of very high voltage gain of 10 power 5. So the voltage gain of 1 lakh around is required. So no single transistor amplifier stage configuration like CE, CB amplifier or CC amplifier can satisfy these conditions. So no single transistor amplifier stage will have all these three characteristics like high input impedance, low output impedance and high voltage gain. So in the previous class we have already studied that CC configuration is going to provide, CC amplifier is going to have a very high input impedance but no voltage gain, and the CB amplifier having high and low output impedance. So and the voltage gain is not possible with the CC amplifier, but it is having high input impedance. Similarly, the current gain is not possible with the CB amplifier, but it is having high voltage gain. So the output impedance should be very low and input impedance should be very high, and it should have very high voltage and power gains. So no single transistor amplifier stage satisfies all these three conditions. So we need a cascading of different stages, different configurations of amplifiers to meet the specifications of high input impedance, low output impedance and high voltage gain. So usually the input stage is to provide, we need an amplifier that should provide a required input resistance, very high input resistance. Input stage is required to provide high input resistance, and in the middle stage that stages that are those will provide the required gain, voltage gain, and in the output stage they should provide the stage should provide required output resistance. So accordingly we are going to design a multi-stage amplifier satisfying these conditions. So today we'll see the multi-stage amplifiers having high input impedance. So that is designed to have high input impedance and low output impedance and high voltage gain. So to have this in the previous class we have studied that configuration CC is the first stage, going to provide high input impedance, and in the middle stages we are going to have C amplifiers, that two or more C amplifier stages going to provide a required gain, and in the output we are going to have a CB, so that it is having low output impedance. Output, sorry, in the output stage we are going to have also a CC amplifier, so that is going to provide high and low output impedance. So multi-stage amplifier design, it is nothing but a transistor circuit containing more than one stage of amplification. The multi-stage amplifier is designed that such that the output of one stage is connected as input of the next stage through the coupling device with the help of coupling devices like capacitors or transformers. So the purpose of the coupling devices is to transfer the AC output of one stage to the input of the next stage, and to isolate the DC conditions of one stage from the next stage. See here the figure, the first stage we are giving input and it is coupled to the second stage through coupling devices. There may be a resistor, capacitor or a transformer coupling devices. So the purpose of the coupling devices here is to couple the AC signal, to transfer the signal, AC input signal, AC signal from output of one stage to the input of the next stage, and also to isolate the DC biasing conditions of one stage to the next stage. In RC coupling, so coupling may be achieved in different ways: RC coupling, transformer coupling and direct coupling. Now we will study the gain of a multi-stage, the important terms related to the multi-stage amplifier: the gain, frequency response and bandwidth of a multi-stage amplifier. So these are the important properties of an amplifier. Here the gain is the ratio of, the ratio of output electrical quantity to the input. The output of the ratio of output to the input of the amplifier is called gain. So the gain may be a voltage gain or current gain or a power gain. So voltage gain is the ratio of output voltage to the input voltage. Current gain is the ratio of output current to the input current, and power gain is nothing but the output power to the input power of an amplifier. So the gain of a multi-stage amplifier is equal to the product. So here the gain of a multi-stage amplifier is equal to the product of the gains of the individual stages. So for example, if G1, G2, G3 are the individual gains, voltage gains of a three-stage amplifier, then the total voltage gain G, we have G is equal to G1 plus G2, G1 into G2 into G3. But in practically, that is the product, the overall gain of a multi-stage amplifier is the product of the gains of individual stages. G is equal to G1 into G2 into G3 into so on into Gn for a n-stage cascaded amplifier, Gn overall gain. But in practice, practically the total gain of a n-stage cascaded amplifier is slightly less than the product of the gains of individual stages G1 into G2 into G3 into so on Gn due to the loading effect of the stages. And coming to the frequency response, the voltage gain of an amplifier, that varies with the signal frequency. So it is due to the reactance of the capacitor in the circuit changes with the frequency of the signal. The gain depends on the frequency of the signal to be amplified, because in the amplifier the capacitor reactance is a function of the frequency, hence it is going to affect the output voltage. So that is the curve. The voltage gain depends on the frequency of the signal, input signal. So the curve showing the variation of the gain with the signal frequency of amplifier is known as frequency response. So this is the frequency response. That curve shows the variation of the gain, voltage gain, that is shown on the y-axis, with the frequency of the signal on the x-axis. So the gain is maximum in the mid frequencies. If you see that graph, we can observe that the gain is maximum in the mid frequencies, and the gain falls at low and high frequencies. We will study later the reason why the gain falls at low and high frequencies. The gain of the amplifier increases as the frequency increases from 0 to till it becomes the maximum, called resonant frequency. The frequency of the signal increases beyond this FR, resonant frequency, the gain again decreases. So the performance of amplifier depends upon its frequency response. So while designing an amplifier, we should take an appropriate steps to ensure that the gain is essentially uniform over the operating frequency range, because the gain is a function of a frequency. So the gain should remain constant in the desired region of operation of the amplifier. So for example, the audio amplifier we consider, which is used to amplify the speech or music. So it is necessary that all the frequencies, the bit falling between 20 Hz to 20 kHz, should amplify without distortion, uniformly amplified, all the frequencies ranging from 20 Hz to 20 kHz without distortion. Uniformly, they should amplify uniformly without distortion, otherwise speaker will give a distorted sound output. So that means the frequencies range from 20 Hz to 20 kHz audio frequency range. If it is audio frequency amplifier, then all the frequencies falling from between 20 Hz to 20 kHz should be amplified uniformly. The gain of all the frequencies falling between 20 Hz to 20 kHz should be the same for any frequency. All the frequencies between 20 Hz to 20 kHz, the gain should be constant or uniform throughout this range for an audio frequency amplifier. Otherwise there will be a distortion. If it is not, the gain is not uniform for the frequencies, for all the frequencies between 20 Hz to 20 kHz, so there will be a distortion in the sound output. So that is the importance of frequency response, or the bandwidth, that we call it as a bandwidth of the amplifier. The range of bandwidth, nothing but the range of frequencies over which the gain of an amplifier remains constant or uniform. In general, the gain of the amplifier is represented as a number because it is the ratio of output quantity to the input quantity. And it is represented in the dBs. Because we know the gain of a multi-stage amplifier is the product of the gains of the individual stages. So it is going to be a number value having more number of digits. Difficult to remember those digits when it is very large, when the gain of a multi-stage amplifier is very large or very small. So that can be represented by using less number of digits using logarithm scale. So the power gain or of a gain in decibels, we have the relation that is 10 log of P out by P in. That is the expression showing the gain in dBs. Gain in dB, that is equal to 10 log of P out by P in to the base 10. So that we call it as 1 bell is equal to 10 dB. So power gain, we have the relation 10 log of P out by P in to the base 10. If the two powers developed in the same resistor are with the equal resistance, then so P1 is equal to V in square by R or I in square into R, or P2 is equal to V out square by R I square R. So we have a gain, voltage gain in dB. So that voltage power we can represent in terms of voltage V square by R. So voltage gain in dB 10 log of V square R by V out square by R divided by V in square by R. So that is R gets cancelled. So we have 20 log of V out by V in to the base 10. That is the expression for voltage gain. Similarly, the current gain. So current power of a circuit is represented in terms of current by I square R. So 10 log of P out by P in to the base 10 we can represent in terms of current 10 log of I square I out square by I out square into R divided by I in square R. R gets in the numerator, in the denominator R gets cancelled. So we have I out by I in, 20 log of I out by I in is the formula of current gain in dB. So advantages of repressing the gain in dB. So dB is the logarithmic unit. Our human ears responds the sounds in logarithm scale. That is, the loudness of sound heard by our ear is not according to the intensity of the sound, but according to the logarithmic intensity of the sound. So thus, if a intensity of the sound given by a speaker is increased 100 times, our ears hear a doubling effect. That is log 100 to the base 10, that is equal to 2. That is, if the sound increases, intensity of the sound increases by 100 times, our ears hear the sound, that is gets doubled. So as loudness were doubled, instead of made 100 times, hence the units of gain tallies with the natural response of the ears. So when gains, also we have another advantage, that gains are expressed in dB. The overall gain of a multistage amplifier is the sum of the gains of individual stages. So when we have the gain of multistage amplifier in normal scale, that is the product of the gains of individual stages. So doing product is somewhat difficult than doing addition. So when we convert the gain of a multistage amplifier in dB, then we can simply add the gains of the individual stages in dB to get the gain of multistage amplifier in decibels. So the overall here, that is the overall gain of a multistage amplifier is the sum of the gains of individual stages in dBs. So easily we can add the gains. Simply adding the gains of individual stages in dB will get the overall gain of multistage amplifier in dBs. So that is the advantage of representing gain in dBs. Coming to the bandwidth of a multistage amplifier, it is the frequency over which the voltage gain is equal to or greater than the 1/√2 times of the maximum gain, is the range of frequencies over which the voltage gain is equal to or greater than 1/√2 times of the gain, maximum gain, that is known as the bandwidth. It has been found that if the gain falls to 70.7% of the maximum gain, the ear cannot detect the change. For example, if the gain of an amplifier is 100, then even if the gain falls to 70.7, the ear cannot detect the change in the intensity of sound, and hence no distortion will be observed by our human ear. However, but the gain falls below 70.7, the ear will hear clear distortion. So the range, that is the point we have taken, that the range of the gain, maximum gain, when the range of frequencies greater than or equal to the 70.7% of the maximum gain corresponds, the range of frequencies corresponds to the gain greater than or equal to 70.7% of the maximum gain comes under the bandwidth of the amplifier, because any change that happens in between this range above or greater than 70.7% of the maximum frequencies, the point of frequencies at which the gain remains greater than or equal to 70.7% of the maximum gain, our ears cannot detect the changes, so we'll not going to have any distortion that will be heard by our ears, human ears. So that range we considered as the bandwidth of the amplifier. Observing the frequency response curve, any frequency lying between f1 and f2, gain is equal to greater than the 70.7% of the maximum gain in the frequency. See here. So any frequencies, all these in this range between f1 and f2, the gain remains here. This is the gain, this is the portion of gain where gain remains greater than or equal to 70.7%, greater than or equal to 70.7%. This is the range 70 point of the maximum gain. So this range we call it as bandwidth. This range we call it as a bandwidth of the amplifier, and we can see that f1 and f2 are the known as the limiting frequencies, where f1 is called the lower cutoff frequency and f2 is known as upper cutoff frequency. So the bandwidth of an amplifier can be also be defined in terms of dB. Suppose if the gain of the amplifier is 100, then 70.7% of its, if it is 70.7, so the fall in voltage gain from maximum gain 20 log of 100 minus 20 log of 70.7, so that we can write 20 log of 100 by 70.7 to the base 10, 20 log of 1.414 to the base 10, that will become in 3 dB, the value will become 3 dB. So hence the bandwidth of the amplifier is the range of frequency at the limits of which its voltage gain falls by 3 dB from the maximum gain. The frequency f1 and f2, also called as 3 dB frequencies, are half power frequencies. So in the range from 70.7 to the maximum, the difference is only the 3 dB. Hence that this range we call it as 3 dB range or 3 dB, and the frequencies corresponding to this range are called 3 dB frequencies. F1 and F2 are 3 dB frequencies are off power frequencies. The 3 dB here comes from the value, the voltage gain at this frequencies is 3 dB below the maximum value. In this range, the voltage gain of all frequencies between F1 to F2 will be less than 3 dB from the maximum. When the voltage gain is falling below 7.707 of its maximum value, voltage will fall 1 by root 2 times of its maximum. Hence they are called as off power frequencies or 3 dB frequencies. So we will going to solve few problems on the gain and bandwidth frequency response of a multi-stage amplifier. Before going to this, says find the gain in dB in the following cases: the voltage gain of 30, the power gain of 100. Calculate the gain in dB. Voltage gain of 30, so 20 log of 30 to the base 10 it will come, that is 29.54 dB. Power gain of 100, that we in dBs, power in dB, 10 log of 100 to the base 10, so it is 10 power 10 log of 10 power 2 to the base 10, so it is 2 into 10, that is 20 dB. Similarly express the following gains as a number. So when gains are given in, so in this case we have converted the gains into dB. In the next example, if gains are given in dB, then we'll convert them into normal. Let us consider the power gain of 40 dB and power gain of 43 dB convert into normal. How to convert the dB scale into normal gain? Power gain of 40 dB, so we can 40 dB is equal to 10 log of P out by P in. So 40 we can write 10 into 4, so we can write 10 log of P out by P in to the power of P out. In place of P out by P in, the ratio we have 10 power 4. So anti-log of 4, that is 10 power 4. Ten power 4 is equal to 10,000. So power gain of 43 dB. (43 dB), 10 into 4.3, So anti-log of 4.3, that is equal to 2 into 10 power 4, 20,000. So 10 log of P out by P in is equal to 43 dB. 10 log P out by P in is equal to 43 by 10, that is 4.3. So P2 by P1 is equal to 10 to the power of 4.3, that is 20,000. A 3-stage amplifier has a first stage voltage gain of 100, second stage voltage gain of 200, and third stage voltage gain of 400. Find the total voltage gain in dB. First stage voltage gain in dB, that is 20 log of 100. First stage having a gain of 100, second stage 200, and third stage 400. 100, 200, 400. So 20 log of 100, that is 40 dB, and 20 log of 200, into 2.3, that is 46. 20 log of 400, that is 20 into 2.6, 52 dB. So the total voltage gain of a 3-stage multi-stage amplifier is the sum of the gains of individual stages, in dBs. So we have 40 plus 46 plus 52, it is 138 dB, the overall gain of a 3-stage amplifier. Now another problem, we'll see. A multi-stage amplifier employs 5 stages, that is n is equal to 5 number of stages, each of which has a power gain. Each stage has a power gain of 30. What is the total gain of amplifier in dB? So each gain of each stage is 30, and such that we have 5 stages. The power gain of one stage, 10 log of 30. Each stage is going to have a gain of 30 dB. So 10 log of 30 to the base 10, 14.77. So like that we have 5 stages. So the total power gain is 40, each stage is going to contribute 14.77 dB. So that we have, like that we have 5 stages, 14.77 into 5, 73.85 dB, the total power gain. And if a negative feedback of 10 dB is employed, find the resultant gain. So negative feedback with negative feedback, power gain with negative feedback, 73.85 minus 10, 63.85 dB. Another example, an amplifier. The output power is 1.5 watts at 2 kHz and 0.3 watts at 20 kHz, while the input power is constant at 10 milliwatts. Calculate by how many decibels gain at 20 Hz is below. that at 2 kilohertz. Calculate how many dB gain at 20 hertz is below that at 2 kilohertz. So we have to calculate the gains at 20 hertz and 2 kilohertz. At 2 kilohertz the output power is given 0.3 and the input power is 10 milliwatts. In the two cases input power is same 10 milliwatts, but the output power is changing with frequency, output voltage. So output power at 2 kilohertz is 1.5. so we have power gain at this frequency 2 kilohertz. Power gain in dB at 2 kilohertz can calculate 10 log 1.5 watts by 10 milliwatts to the base 10, it is 21.76 dB. Similarly we can calculate the power gain at 20 hertz. The output power is only 0.3 watts, so 0.3 10 log power gain in dB at 20 hertz, 10 log of 0.3 divided by 10 milliwatts to the base 10, it is 14.77. so it is the difference. The gain from 22 kilohertz to 20 hertz is 21.76 because when the frequency is decreasing from 2 kilohertz to 20 hertz, frequency is decreasing, gain falls. So how much of gain is falling from 2 kilohertz to 20 hertz? That is the difference of gains at 2 kilohertz to 20 hertz in dB, that is 21.76 minus 14.77, it is 6.99 dB. Another example, a certain amplifier has a voltage gain of 15 dB. If the input signal voltage is 0.8 volts, what is the output voltage? Here the gain is given in dB, so we have 20 log of V out by V in to the base 10 is equal to 15 given, and the voltage V in is also given 0.8, so we have to find V out. So 20 log of V out by V in to the base 10 is equal to 15 given, and V in is 0.8. Fifteen is equal to 20 log of V out by V in, so that is 15 by 20 is equal to log V out by V in, V out by 0.8 to the base 10. So we can write V2 by 0.8 is equal to 10 to the power of 0.75. So V2 is equal to 0.8 into 10 power 0.75, it is 4.5 volts. Another example, an amplifier has an open circuit voltage gain of 70 dB, and output resistance of 1.5 kilo ohms. Voltage gain and output resistance is given. Determine the minimum value of load resistance RL so that the voltage gain is not more than 67 dB. Open circuit voltage gain 70 dB given, and the output resistance is given 1.5. so we need to find the load resistance such that the gain should not increase more than 67 dB. So A0 is given 70 dB and AV output voltage 70 dB and AV is 67 dB. So the difference in gain, that is 70 minus 67, that is 3 dB. 20 log of A0 minus output gain or open circuit voltage gain A0, and 20 log of AV, that is 3 dB. 20 log of A0 by AV is equal to 3 dB. A0 by AV is equal to 10 power 3 by 20. that is 1.41. So AV by A0 is equal to RL by Rout plus RL, because the voltage gain is proportional to their load resistances. So AV is the corresponding to the RL and A0 is the overall output voltage gain, Rout plus RL. RL we don't know, so substituting Rout, AV by A0 is 1.41, from which we can calculate RL, that is equal to 3.65. Very important relation, that is AV by A0 is equal to RL by voltage gain, and the overall voltage gain of a stage depends on load resistance, and overall voltage gain depends on the output resistance and also the load resistance. Another example, an amplifier feeding a resistive load of 1 kilo ohm has a voltage gain of RL is given and voltage gain of 40 dB. If the input signal is 10 milliwatts, RL Vout for voltage gain is given and in dB, and Vin is given. So we need to find Vout. Vout is equal to Vout by Vin is equal to 10 to the power of dB gain divided by 20, 40 divided by 20, 10 power, so that is 100. So Vout is 100 times of the input voltage, that is 1000 millivolts or 1 volt. So important, the load power is equal to Vout square by RL. So Vout is 1 volt by RL is 1000, that is 10 power minus 3 watts or 1 milliwatt. So very important, that is load power. Power is equal to V square by RL, Vout square by RL. Vout we have already calculated from the formula, 20 log of Vout by Vin to the base 10, that is equal to 40 dB given. Calculate output voltage and substituting output voltage in the load power equation, P is equal to V square by RL, and RL is given, so the 1 milliwatt. An amplifier rated at 40 watts output is connected to 10 ohm speaker. Calculate the input power required for full power output. Input power we have to calculate. If the power gain is 25 dB, and also calculate the input voltage rated for rated output if the amplifier voltage gain is 40 dB. Output power of amplifier is 40 watts given. Power gain is 10 log of P out by P1. So power gain 25 dB is equal to 10 log of P out is 40 watts. Calculate P1. P1 is 126.5 milliwatts. In the second example, calculate the input voltage for rated output. Output rated 5. It is 40 output voltage 40. So voltage gain 20 log of V2 by V1. V2 is 40. Voltage gain of 40 dB is given, V2. So 40 is equal to 20 log of V2 by V1. V2 by V1 90 log of 40 by 20, that is 2, that is 100. So V2 is equal to, so we have a power 40 watts, power output 40 watts. So power is equal to, we know the output voltage, we know the power and also the resistance. So we have to calculate the V2, that is 20 volts. So V1, V2 by V2 by V1 is equal to 100. We have given, it is given. V2 is 20 volts. So V2 by 100, that is 200 millivolts is the input voltage required. Similarly, an amplifier, the maximum voltage gain is 2000 and occurs at 2 kilohertz, and it falls to, it is the problem based on the frequency response. Voltage gain is 2000 and occurs at 2 kilohertz. It falls to 1414 at 10 kilohertz and 50 hertz. Find the bandwidth, lower cutoff frequency and upper cutoff frequency. So it is the frequency response. Maximum gain is 2000 and it falls to 1414 at 50 hertz and 10 kilohertz as shown in this figure. So gain falls to 1414 at 50 hertz and 1414 at 10 kilohertz, and maximum gain is 2000. The maximum gain is 2000. Then 70.7% of this gain is 0.707 into 2000. It is 1414. So it is given that the gain is 1414 at 50 hertz and 10 kilohertz. So we know the bandwidth is the range of frequency over which the gain is equal to or greater than 70.7% of maximum gain. So bandwidth is 50 hertz to 20 kilohertz. It is the bandwidth. The frequency at which the voltage gain of the amplifier exactly 70.7% of the maximum gain is known as lower cutoff frequency in the lower side. So lower cutoff frequency is 50 hertz. So at this frequency exactly the gain falls to 0.707 times at 50 hertz, and at 10 kilohertz the gain falls in the high frequency region, the gain falls to 70.7% of 2000. So this 10 kilohertz is known as upper cutoff frequency, because the frequency on the higher side, output side, the gain, voltage gain of the amplifier exactly 70.7, that is 1414. It comes exactly equal to 1414 at 7, that is the product of 70.7% into 2000 will get 1414. So it is the upper cutoff frequency. So the bandwidth of the amplifier is 50 Hz to 10 kHz. Therefore, it will amplify the signals frequencies lying in this range from 50 Hz to all the frequencies fall in between 50 Hz to 10 kHz will be amplified uniformly without distortion by the amplifier. Hence, it is known as the bandwidth of the amplifier. Properties of dB power gain. These are the useful rules for our dB power gain. For each time the ordinary power gain decreases by a factor 10 of 10, the dB power 10 power 0, 10 power 1, 10 power 2, like that, 10 log of P out by P in to the base 10. If P out by P in ratio increases or decreases by a factor 10, then the gain increases or decreases by 10 dB. The ordinary power increases, for example, from 100 to 1000 by a factor of 10. The increase in power gain in dB, 10 log of 1000 minus 10 log of 100, that is 30 minus 20, that is 10 dB. When the gain increases by a factor of 10 or decreases, the dB increases accordingly. Each time, another advantage of power gain in dB, each time the ordinary power gain increases or decreases by a factor of 2, the dB power gain increases or decreases by 3 dB. Suppose example, the power gain increases from 100 to 200 by a factor of 2. So increase in power in dB, power gain, 10 log of 200 minus 10 log of 100, that is 23 minus 20, it is 3 dB. So when the power increases from doubled, the gain is simply increases or half. When it decreased to half, there is a change in power of 3 dB. Similarly, voltage gain representation, when the ordinary voltage gain increases or decreases by a factor of 10, the dB voltage gain increases or decreases by 20 dB. Suppose the voltage gain increases from 100 to 1000 by a factor of 10. The increase in dB voltage gain, 20 log of 1000 minus 20 log of 100, 60 minus 40, it is 20 dB. Voltage by 20 dB. Each time the ordinary voltage gain increases or decreases by a factor of 2, the dB voltage gain decreases by 6 dB. The voltage gain increases from 100 to 200 by a factor of 2. 20 log of 200 minus 20 log of 100, it is 6 dB. So this we can come to know the dB value. Simply we can assume that increase or decrease in the power in dBs. Whenever there is increase or decrease in the power gain or voltage gain by a factor of 10. So we'll stop here today. So in this class we have studied the definitions. What is the gain of multi-stage amplifier? Definition. of gain of multistage amplifier, bandwidth and frequency response, and the expressions for the gain and the bandwidth. And we have calculated some few problems related to gain, bandwidth and frequency response of a multistage amplifier.